Hi, folks. Welcome back to part 2 of 1.4. So we've been talking about function compositions and ways that we can combine functions with just adding, subtracting, dividing, multiplying. But what we're going to focus on now is this function composition part. Okay, and that's exactly what we did in the last example, where we use the output of one function as the input of a second function. And so what I think is important for us to do right now is make sure we understand how to write this, what it might look like, and then write for ourselves what it means in words, okay? So one way that we could see it is, we saw this on the previous page, f parentheses g parentheses x, okay? Now this meant that we take our g of x function, we put it inside our f function. But another way to write this is like this: f little circle g of x, all right? So this little circle is the symbol for composition. And we don't want to confuse that with multiplication, okay? Now, let's write out in words what this means, okay? So this means find g of x, input g of x into f of x. All right, so we're putting the g into the f. The other way that we might see things is people might switch the order. We might see g parentheses f parentheses x. And the way we would write this with the little circle is we would say g little circle f of x, or we say g composed with f. And if this is the order, we would find f of x first, and then input our f of x into our g of x, right? So the order in which it happens is reversed. And then one way to think about it, we're always going to start with the letters on the inside and then sort of work our way out. Or if it's with the little circle notation, we start with the one closest to x, and then we go to the one that's next furthest away. All right. So that's a little bit about the notation. Let's try a few problems now. Okay, so let's try some problems with the notation instead of just the idea like we had from example 3. All right, here's example 4. Consider f of x equals x squared minus x and g of x equals 3x plus 2. Evaluate f of g of negative 2. And so just to remind us, this question also could have been asked as f composed with g of x. That's another way I could have asked the same question. Instead of the x, though, I would put the number, which is the negative 2. Okay. So we can actually break this down into 2 separate problems, really. The first thing we're going to do is find g of negative 2. So that's 3 times negative 2 plus 2, which is negative 6, plus 2, which is negative 4. The second thing we do, we take our output and we put that into the f function, okay? So this is our initial, and then our output of the first function. Now we put that into the second function, right? So negative 4 squared minus negative 4. And one thing you'll notice is I'm really big on putting parentheses in places. And I do this because I tend to make a lot of sign mistakes, but I find that I make less of them when I actively write all of the parentheses there. Okay, so let's do this out. Negative 4 squared is going to give me positive 16. And then a negative 4 is plus 4. We should end up with 20. Okay. 20 is what we get when we take -2, plug it into the G, and then we take that output and we plug it into the F. Okay. All right, let's try another example here. This one looks like this: G of F of -1, which really could be written G composed with F of -1. And this means that we're going to find our F of -1 first. All right, so let's find F of -1. All right, let's go back. And that function was -1 squared minus -1. Wow, it's almost like I want us to practice working with our positive and negative numbers, right? We get 1 plus 1, which is 2. That means when we plug in -1 into the F function, we come out with a 2. And now 2 is the number that we plug into the G function. Okay. Now we're plugging 2 into the G function, which is 3 times 2 plus 2. 3 times 2 is 6. 6 plus 2 will give me 8. All right. So there we have an example where we are composing F with G and also G with F, and thinking about how the order matters and how it's a similar process overall, just depending which function we put the number into first. Okay. All right, so I think it's all fine and good with numbers, but it's also important to practice this kind of stuff with just the equation. Okay, so we're going to take a look at example 5 now, and you'll notice that I don't give you a number for x. That means that our final answer should just be something with x's in them. All right, so we're basically creating the composite function. We're not evaluating them like we were before. Okay. All right. H of m of x is the same as h composed with m of x. And the way that I would do this is pretty similar. All right. First, I'm going to find our m of x, and that's x plus 2. Right. So when I plug in x, what comes out is x plus 2. Now I'm going to take that x plus 2 and I'm going to put that into the h function. Right? So that means that instead of having h of x equals x squared, I'm having h of x plus 2, x plus 2 squared. Okay. Now, this problem is a good time to remember what it means when we square something, right? Squaring something means we take that something and we multiply it by itself twice. In other words, x plus 2 squared is really x plus 2 times x plus 2. In order to distribute everything here, we got to do x squared plus 2x plus 2x plus 4, right? That's our first, our outer, our inner, and our last. And then we can combine some like terms, and we get x squared plus 4x plus 4. Okay. So when I compose these two functions in that order, I get x squared plus 4x plus 4. Well, let's see now what happens when we compose the functions in the opposite order. All right, so m of h of x is the same as m composed with h of x, right? It's always the one closest that we do first. So first, we're going to find h of x, which is equal to x squared, right? So x squared is the output when I put in x. And then the second thing I'm going to do is now I'm going to find m of the output of x squared. And that means I get x squared plus 2, because everywhere I see the x in the m function, I'm going to replace it with x squared. Now, x squared plus 2, I can't simplify anymore, so that is just my composite function. Okay? So taking some time to work with things with the numbers and the algebra and the notation, that's really what we were looking at right here, right? Learning this new notation. How do we do it with numbers and how do we do it with equations? All right, so let's move on to composite functions that we can work with in multiple representations, okay? So we're going to focus first on the algebra piece here, and we're also going to start to talk about how do we find the domain of the composite function, okay? So let's take a look at example 6 here. Consider f of x equals 5 over x minus 1, and g of x equals 4 over 3x minus 2. Find f composed with g of x. So this is just like example 5, right? I want an equation here. Now this is the same thing as writing f of g of x, meaning I'm going to put the g equation into the f equation, okay? And so when I put the g equation into the f equation, I'm really saying f of 4 over 3x minus 2, right? This x went in here, and what came out is this 4 minus 3x, 4 over 3x minus 2. That is the output we put into f. And where is that going to go? Everywhere we see the x, which is in the denominator, that's where we're going to put 4 over 3x minus 2. And it's going to look kind of gross, but that's okay. 5 over, instead of x, it's the 4 over 3x minus 2. Don't forget, we still have that minus 1. Okay, so looks similar to the f equation like we have up here, except the x is the 4 over 3x minus 2. Now, don't worry about simplifying that. This is totally fine for right now, okay? So we're going to leave it like this as our function composition. Now, let's talk about finding the domain of the composite function, okay? And I have a few suggestions for us on how to do this. I would say the first thing that we should do is find any restrictions on the inner function. Okay. In other words, which function did we put inside the other one? So in this case, our g of x is our inner function, okay? So in this case, we're looking at restrictions on g of x equals 4 over 3x minus 2. Okay. And if I look at this equation, a few things might pop into my head. I might remember from when we were talking about domain back in the previous sections, that a fraction is something we should always look for 0 in the denominator, right? That's going to be a problem for us if we see 0 in the denominator. And so for us, what that means is we're going to figure out what number makes this denominator 0. All right. And so we'll get 3x minus 2. We know that that cannot be equal to 0. I'm going to add 2 to both sides. 3x cannot be 2. And I'm going to divide by 3. So x cannot equal 2/3. That means that I could put in any other number, but I just can't put in 2/3 here. Otherwise, I will get a disaster where I'm dividing by 0. Okay. So we found the restriction on the inner function. But after we do that, what we need to do is find the restrictions on the composite function. All right, we need to find the restrictions on the composite function. And this, my friends, is our composite function. Okay. So 5 over 4 over 3x minus 2 minus 1, right? And one thing that we notice here is that, again, we have a fraction, right? This whole thing is a fraction, which means that we can't have 0 in the denominator, right? And we can set up an equation that does that. 4 over 3x minus 2 minus 1, that cannot equal 0. All right, let's see if we can solve for x. So let's start by adding 1 to both sides. 4 over 3x minus 2 cannot be equal to 1. All right, I'm going to multiply both sides by 3x minus 2. 4 cannot be equal to 3x minus 2. I'm going to add 2 to both sides. So 6 cannot equal 3x. And I'm going to divide both sides by 2. So x cannot equal 2. All right. So first we check the restrictions on the inner function. Can't have x equal to negative or to 2/3. Then we check the restrictions on the composite function. X can't equal 2. So that means we want to write the domain as everything except for those two numbers. So here's how we write it. Domain, negative infinity to 2/3. But we can't have 2/3, so we write a parenthesis. In union with 2/3 to 2. And we can't have 2, so we need another parenthesis. In union with 2 to infinity. Okay, so this is what our final answer looks like. Now, I just want to write maybe a possible answer that folks might write. So I can imagine someone might write negative infinity to 2 in union with 2 to 2/3 in union with 2/3 to infinity. Okay. Now, I understand that we've got the correct numbers in here, but really we like to list these numbers from the smallest, which is negative infinity, all the way to the biggest, which is positive infinity. So that's why we're going to have the 2/3 first, and then we have the 2, because 2 is bigger than 2/3. Okay, so we want to make sure we line these up in order from smallest to biggest. All right, so that, my friends, is how we find the composition of two functions and then also find the domain of the composite function. All right, we've got one more example below that's very similar, example 7. So this is a good time to pause if you want to try this one by yourself and then come back and watch the video to see the explanation. All right, so I'll give you a moment to pause if you'd like. All right, if you're still here, let's figure this one out. So find G of G composed with f of x. That's the same thing as saying G, but instead of putting in x, we put in f of x. All right, so we're putting the f function inside the G function. All right, and so this is going to give us G of the square root of x plus 4. This is my output. And then everywhere I see the x in the G function, I'm going to replace that with the square root of x plus 4. This is going to give me 1 over the square root of x plus 4, and then outside of that square root, minus 2. Right? So I took x, I plugged it into the f equation, and then I took that output and put it into the g equation. All right, let's see if we can find our domain for this function. Okay, we're going to do the same thing. We're going to start by finding the domain of restrictions of the inner function. All right, in this case, the inner function is f of x equals the square root of x plus 4. All right, so now what does the square root, what is that in terms of domain restrictions, right? For our even roots, and we talked about this a few lessons ago, the even roots, the inside of the root must be greater than or equal to 0, right? Because if I had like a -5 inside the square root of -5 is going to give me what we said was an imaginary number. So we have to say, where does x plus 4, is that greater than or equal to 0? And if we subtract 4 from both sides, we get x is greater than or equal to -4. That means that our domain, we can only choose numbers like -4, -3, -2, -1, 0, anything bigger than -4, or including -4, but we couldn't have like -4.5 or -5, okay? The second thing we need to check is the domain restrictions on the composite function. In other words, our 1 over square root of x plus 4 minus 2. And the reason why I chose this problem is because it's a nice way to check, okay, what happens when we have an even root, right? What is the rule about domain? But then also we get to talk about what happens when we have a fraction and how is that impacted by the domain. All right, so we've got a fraction here, which means our denominator cannot equal 0, right? And so for us, that means square root of x plus 4 minus 2 cannot equal 0, right? And if I add 2 to both sides, I get square root of x plus 4 cannot equal 2. I can square both sides from here. So x plus 4 cannot equal 4. And then last but not least, we can squeeze that in. Last but not least, if I subtract 4 from both sides, I get x is not equal to 0. Okay, so if I put in 0 here, I would end up with 0 in the denominator. So that cannot be part of my domain. So how do we write that it has to be greater than or equal to -4 and it can't include 0? Well, we're going to write it like this. Domain, including -4 to 0. No 0, so parentheses, in union with 0 to infinity, because we can have everything else. All right. So let me go ahead and zoom out so you can see this whole problem on one page, but this seems like a great stopping point for the second part of 1.4.